Welcome to AP Podcast 14.8. This is on salts acting as acids and bases. Now, we're very familiar with salts. They are simply ionic compounds. But it turns out that just in case you're not completely confused by all this acid and base and then acid-base equilibrium, it turns out that some salts will actually act as an acid at times or act as a base. And so it makes it a little more challenging. So we're going to try and get all this stuff straightened out. And this is going to be the podcast where you really got to focus because it gets a little odd. All right. Now, the first thing that we know of is that any kind of cation from a strong base, which of course is group 1 or group 2 metals, or any kind of anion of a strong acid, which is NO3, H2SO4, and so on, we know that those don't do anything in water. All right? They're not going to be attracted to the water. They're just going to be floating around. So those really are not going to affect any kind of pH. There's no equilibrium for them, and we don't even worry about what's happening. What I mean by that is you guys know from solubility rules and all that kind of stuff, NO3 plus water is just NO3 plus water. Sodium ions plus water is just sodium plus water. So what we're saying here, since NaCl since the Cl is the anion of a strong acid like HCl, we know the Cl is not going to do anything. All right, and the NO3 is the anion of a strong acid. It's not going to do anything either. So we don't have to really worry about that. But what we want to do is we want to look at those kind of compounds that actually do affect the pH. And they all affect the pH the same way. Some of them attract the H from water, and some of them give off an H to form an acid. So let's look at basic salts first. All right. Now, if the anion of a salt is the conjugate base of a weak acid, the basic solution will be generated. Woo, that sounds like kind of a technical thing here. But what's important for us? We've got to really focus on weak acids here, all right? And this is why it was absolutely critical that you memorize those 7 strong acids so that you would know what this situation takes place. For example, if we were to take just good old sodium fluoride and dump it in water, right? And that's what we're doing here. Now imagine this is really NaF, right? Well, you guys know what sodium's going to do in water, right? It's going to do nothing. It's a spectator. It's always been a spectator. But what do we know about fluoride? Well, we know that HF is a weak acid, right? And what does that mean, really? Well, that means that this F minus has a high affinity for H's, all right? And so toss some F minus in some water, and guess what? One of those H ions is attracted to the F, causing you to make some HF and some OH. Now, the important thing, though, is look what we have floating around. We have some hydroxide floating around. You guys already know that this isn't going to do much, right? It's a weak acid. It's not going to break up hardly at all. However, the hydroxide is floating around now. So what we have is we've dumped some salt in some water, and if you were to stick a pH meter in there right now, you would get a pH above 7, which seems odd, but it's really what happens. So let's look at how this works. Let's look at the equilibrium expression here. Kb, we've got HF plus OH, right? Here's our products over the reactants, right? So that's what's going on. Now, we don't have a Kb for HF, do we? But we do have a Ka, don't we? And so what we can do is we can use the Ka from HF and figure out the Kb to solve this problem. And let me kind of show you how that works, okay? Imagine if I took a Ka times a Kb right here, and this is just good old algebra stuff. Now, look what would happen if I would multiply those two equilibrium expressions. Well, we've got HF on the top there, HF on the bottom. They cancel, right? And I've got F minus on the bottom there and F minus on the top there. They cancel. So look what happens when you take the Ka and multiply it by the Kb. You're left with the concentration of hydroxide and the concentration of hydronium. This is a very, very important relationship because what this allows us to do is figure out either Ka or Kb if we know the other one. All right? Because we always know Kw. So this is a really important idea. So if you know the Ka for an acid, you can find the Kb of its corresponding salt when that acid is in water. And we're going to do that. So let's look at this problem, and I'll show you exactly how we do this. All right, so here's our problem. So if I were to think about how to do this, let's think about what's going to happen. First of all the ions and all the major species involved, we're going to have some of this, right? We're going to have some of this, and of course we're going to have water. Okay. Well, what's sodium going to do in this situation? Nothing, right? It's going to be a spectator. But here we go. Fluoride plus water is going to give us, and this is an equilibrium, is going to give us HF plus OH minus, right? And then if I write out that equilibrium expression, because I'm finding a base, it's a Kb, and that equals my concentration of HF over OH. Did I really put a plus there? Sorry, guys. Thanks for yelling at the screen and telling me I messed up. Over F minus. Okay? So now I've got the Kb expression. However, I don't have a Kb for F minus, do I? So what could I possibly do? Well, I know that Ka times Kw, or Kb, I'm sorry, equals Kw, right? So if I take Kw, which in this case is 1 times 10 to the minus 14th, and I divide that by the Ka of HF, and I will pause, I gotta look, okay, it's 7.2 times 10 to the 4th. I get a Kb that equals 1.4 times 10 to the minus 11th. All right, so now I've found my Kb. And let's see, what do they want us to find? They want us to find the pH. So, like always, we're going to solve for x up there. So, instead of me working out just in the, in the interest of time, when I work this out, I get an x value that equals 2.0 times 10 to the negative 6. And again, if you want to calculate that out and make sure I didn't mess up, that's fine. But that's the value I would get. All right. Now, remember, again, this is a Kb, and so where we got to focus on, that's an OH concentration, right? So I just take the negative log of that, subtract that from 14, and then I get a pH of 8.31, right? So that's a basic salt. Pretty interesting stuff, though. Look, I just dumped in some sodium fluoride. All of a sudden, the pH went up. And the reason it went up is because you guys know that fluoride is highly attracted to H, and so it makes them HF and OH. Okay, how's that? All right, so let's move on to acidic salts. Okay, the salt with a cation of a weak base and the anion of a strong acid will be acidic. Right. We do the same thing we did before. Now, look at this problem. Calculate the pH of a solution of 0.1 molar ammonium chloride. Now, most often, you're going to get ammonium in the examples we use. Okay, think about what ammonium's going to do in water. NH4 plus, pardon me, not in water, pardon me. It's just going to break into NH3 and H plus. Now we're faced with the same issue as before. Okay, we want to find the Ka of this, right? However, look what they've given us. They've given us the Kb of ammonia. So just like the last problem, I mean, if I'm going to write out this equilibrium expression, it's going to look like this: NH3 plus H plus, right, over NH4 plus. Okay? So if I'm going to write this out and work this problem out, I need a Ka. However, I don't have a Ka. I have a Kb. And so just like before, I'm going to take that Kb and divide it, remember my Ka, I'm going to divide that Kw by my Kb, and I'll get an answer. And then I can solve this problem. All right. So it's different ways of looking at it. We'll practice these in class, but the thing is you almost have to think backwards on this. But that's why it's important that you think about the chemistry, that you really focus on what's happening when this is in water. You can't memorize these. These are too hard. So you got to look what's going on in water. Is it going to give off an acid like this one is? Give off an H? Or is it going to attract an H from water and give off OH? Super, super important. And then I have one more bullet here. Other acidic salts are those of highly charged metal ions, and we will talk about that in another podcast. So let's just look at this one last thing because I've got a couple things. Salts with acidic and basic ions. Now, imagine you've got a compound that has both acidic and basic ions. Ooh, what in the world could happen there? Well, let me give you an example. Let's say I have ammonium cyanide. Ooh, okay? Now, what's this going to do? That's going to give off an H+, right? What's that going to do? That's going to attract an H and give it off an OH. So how in the world could I solve this problem? Well, what we have to do there is we have to look at the Ka's and Kb's, all right? So if the Ka is greater than the Kb, it's going to be acidic solution. If the Ka is less than the Kb, it's basic, and if they're equal, they're neutral. Right? So based on that, let's go ahead and look at this. Okay. Now NH4 and C2H3. Let me see this one. I think I have that memorized. I want to say it's 1.8 times 10 to the minus fifth, or I should say that's what NH3 is, right? Okay, and so this thing, if I divide that into the K, W, I get a value of 5.6 times 10 to the minus 10th for the Ka, right? And then for this one, this is acetate. Oh, wait, that's one. Okay, so acetic acid is 1.8 times 10 to the fifth. So again, dividing it back there. So this is going to be neutral. All right. Let's see. Let's do another one. NH4. Well, I already know the Ka for this thing, right? 5.6 times 10 to the minus 10th. The Ka for HCN. Let me find it here on my chart. The Ka for HCN. All right. So the Kb for this guy right here is 1.6 times 10 to the negative fifth. So if you look at that situation, the Kb is bigger, so this solution would be a basic solution. All right? And then this last one, we've got aluminum sulfate. All right, so the Ka for aluminum, like hexa aqua, it's the when we had 6 waters attached. The Ka for that was 1.4 times 10 to the minus fifth. Okay, and then for sulfate, the Kb is 8.3 times 10 to the minus 13th. So this thing would be acidic. All right, so there you go. Okay, so hey, we're going to practice a lot of problems with this acid-base salt stuff because this is really confusing to people. And I will see you in class, and we're going to get good at this, so don't panic. See you next time.